like d by dt for all your states equal a times all your states, right? This is a state space model. What is my states? What's your state vector? What are your states here? Or how many? What are your states? Come on guys, what are your states? Yeah, you have exactly, you have whatever coming from structure, whatever coming from aerodynamics. So in structure we have 4 states that have physical meaning. By construction, aerodynamics we have 2 states, but they don't have physical meaning, right? X aerodynamic 1, X aerodynamic 2. They just the states of the controllable canonical form realization of this transfer function. It has nothing, no meaning. Okay, so let's fill in this guy. All what I have is just these 2 equations now. Don't look or don't think outside. I just need to fill in this thing. So let's do it. X structure dot equals. Here is the equation for X structure dot. And please follow me, because I will do it. I will not take my time to do it. I will skip some steps. So X structure dot, here it is. It's A structure times X structure. So here is A structure times X structure. Okay? Any question about this term? And then we have B structure times something. Anything other than these 2 states, you have to replace it with something in terms of the states. So B structure times this guy, I will replace it. Obviously, I will replace it from this equation. So B structure from here times whatever coming. Times what? Times FA XA. Very good. So B structure times FA, this multiplied XA. Very good. The second term, please follow me. B structure times HA times this guy. Again, this is neither one of the states. So I have to replace it. I will replace it from here. So B structure H arrow times Fs. B structure times F arrow times H arrow, times Fs. B structure H arrow Fs. This is all multiplying X structure. So this is why I put it here, because it will multiply X structure. This is the filling of the first line. You can take your time to substitute the equations and make it clearer to yourself if you like. Okay. The second equation for XA dot, here is the equation of XA dot, is A aerodynamic times X aerodynamic. Here is A aerodynamic times X aerodynamic. Plus B aerodynamics times this red guy, V3/4. So I will get V3/4 from here, so this is a bit simpler. B aerodynamic times F structure. B aerodynamic times F structure, and again it's multiplying X structure, so this is why I put it here to be multiplying X structure, and I'm done. This is the combined model. So indeed, this is X total or X aeroelastic is equal to A total, or A for the aeroelastic system combined. And this is X total. This A aeroelastic depends on U, as you can see clearly. So how many states in total do I have here? 6. So you expect how many eigenvalues? How many eigenvalues do you expect? It's 6 eigenvalues. The structure alone has 4. These were like 4 of the structures from before. They move like this. But of course the motion is changing because of the coupling. And the aerodynamics has 2, and there are 2 rear roots. They move like that as U increases. Again, I'm looking for the value of U at which this happens. If you do this for the example that we're studying you will get something like, maybe something like this, feet per second. As you can see, it's much larger than the quasi-steady. It's to me, it's astonishing. It's a fact. Just changing the model a little bit, instead of using quasi-steady, just use unsteady. It makes this significant change from 200 to 1,000, 5 times flutter speed. Because remember, if your real flutter speed is 200, or if you believe that your flutter speed is 200 as an airplane designer, what you will do? You cannot fly slower because this is a mission requirement. So you will go and modify your design. You will add more weight to structure, which is huge penalty to your design, right? Or do a control system or whatever. I mean, you will do something to prevent this from happening because the cruise speed is a mission requirement. You cannot sacrifice that. And if your flutter is below, if it is below the mission requirement, you cannot fly. So you will do whatever it takes. Like what I said in the 60s. In the 60s, they used to add lead. This is the worst thing to do in an airplane, right? To add lead, right? They add lead to the leading edge to shift the CG forward to prevent flutter. This is the best solution that they had at the time, which is not efficient. Okay. So now, if the analysis shows you that already your flutter speed is much higher and you're good to go, then that's a good thing to have. The K flutter, like I said, this is omega flutter, and the K flutter here is something like 0.32. If the unsteady analysis shows you it's 0.3, the K, it means it's unsteady, right? If it's 0.1, 0.05, then quasi-steady might have given you a good answer already. But this is 0.3, it's unsteady, it's truly unsteady flow. Okay, as you can see, there is really a value of writing down a state space model for aerodynamics. It's no longer 2 pi algebraic, it has a dynamics, it's a state space model. What is the value? 2 values. First, it's very easy in simulation. Just do LSM in MATLAB, LSM command. Very easy in simulation to whatever input, to whatever angle of attack you have. Very easy in simulation. Second, it is very convenient when you couple with a structured dynamic model or the flight dynamics of the entire airplane. It doesn't have to be structured. It can be, well, you might have rigid wings and you just ignore structure, but your airplane is maneuverable and does agile maneuvers, and you want to analyze the airplane flight dynamics, the equations of motion that we used to have in 175. You analyze the flight dynamics not with quasi-steady aero, but with unsteady aero. So what you're going to do? Well, you have your state space model for flight dynamics, and here is a state space model for aerodynamics. Just couple them together in the exact same way we did here. So this is very convenient. And we're done with today, and actually we're done with the time, but I have to show you the projects. So I'll take about 5 minutes, hopefully, to talk about the projects.